Okay, welcome back everybody for the last lecture of the week. Kate just uploaded the PDF of her slides to the Slack if people want to prefer to follow along on their own screen. Kate says she's going to introduce herself, but this is Kate Pattle, and she's an expert in magnetic fields in the Milky Way and in nearby galaxies. And I'll leave it to you, Kate.
Thank you very much. And thank you very much to the organisers for asking me to give this lecture. My name is Kate Pattle. I'm a lecturer at UCL, University College London. Before that, I bounced around a bit. I did my PhD at the University of Lancashire. Then I did postdocs in Taiwan and Ireland before ending up at UCL. And for most of that time, I've been working on magnetic fields, which is an absolutely great question. Sorry, an absolutely great topic to work on if you want to preempt everyone's favorite seminar question, which is, but what about the magnetic fields? Sure, it's been something that you've all been dying to know the answer to. So if you haven't come across this yet, there's a bit of a joke that if you have gone to your department seminar, fallen asleep at the back and woken up just for the big round of applause at the end, and you want to really throw the speaker off, you put your hand up and say, but have you considered the effect of the magnetic fields? And everyone's instantly flummoxed. But magnetic fields thread the interstellar medium on all size scales. So much as we might want to pretend otherwise, we do need to understand what dynamical role they play in the evolution of the interstellar medium in the star formation process. To be clear, this is absolutely not a question I'm going to answer in the next hour and a half because we absolutely don't have an answer to this yet. But I can show you how, over I'd say the last decade or so, there's been an absolute wealth of new observations that have really started to help us answer this question. So just to demonstrate the point that we're starting from, this is probably my favorite quote, which is from Ludwig Volcher, who in 1967 said, "The argument in the past has been a process of elimination. One observes a phenomenon, you explain the part that you can explain, and then the unexplained part is taken to show the effect of the magnetic field. It therefore follows that the larger one's ignorance, the stronger the magnetic field." Now, you'll note he said the argument in the past has been in 1967. I would argue that we haven't moved until fairly recently. Maybe we were continuing in this vein, but I think despite all of what I'm saying, this is no longer true. We are genuinely able to investigate what magnetic fields are doing in the interstellar medium, what role they're playing, and how important they are through a mixture of ever-improving simulations and also the observations that we've got over the last decade or so, and we'll be getting more of, hopefully, in the future. So this is the outline of my talk. I'm going to start by walking through the MHD equations. I've front-loaded all of the maths. Once we get past section 1 in this, there's really not going to be very much maths, I have to admit. Then I'm going to talk a bit about how we actually measure the interstellar magnetic fields, and then what we think we know about magnetic fields on cloud scales, filament scales, and star-forming core scales. I'm then going to very briefly talk about the, I think, quite new topic of how magnetic fields and feedback from star formation interact with one another. I will very briefly touch on magnetic fields and galaxies other than the Milky Way, and I'm going to finish by just talking about what's coming down the line, facilities-wise, to help us answer the questions that I'm going to be talking about. So, starting with the maths. So this is actually, I think, quite elegant, the relationship between magnetic fields and gas flows in the interstellar medium. So I really am starting at the beginning here with Maxwell's equations, which I'm sure everyone's painfully familiar with. We start with Gauss's law. Our favorite here, Gauss's law for magnetism, div B is equal to 0, no magnetic monopoles. We've got the Faraday's law of induction, and we've got Ampere's circuital law. Some of them just mention the electric field, some of them just mention the magnetic field. The last two couple them together. What we'd really like to do, if we want to talk about magnetic fields in the interstellar medium and make our lives easy, is just express the evolution of the of magnetic fields in the stellar medium without having to have the electric field anywhere in these equations. We can do that by looking at this other equation, the Lorentz force. I hope and trust I got all the vectors the right way around here, but if you disagree with me, then do tell me. So this is the force on a moving charge, which depends on the electric field and magnetic field. And then we've got Ohm's law, so resistivity. So we've got our electric current density, current per unit area, expressed in terms of the electric and the magnetic fields, and also the velocity of whatever it is we're considering. So I'm going to flash through the derivations on the next few slides, absolutely not intending that you do it in your head as we go along. This is just showing the direction that it goes in, and do take a look later if you're interested and you want to work it all through. It does genuinely work. So what we want to do is eliminate the electric field from these equations. And we really want to eliminate it from Maxwell's third law. So to do that, we start by assuming that we're dealing with non-relativistic plasmas, and we can have div of B expressed in terms of current density J up here. We can then use a rearrangement of Ohm's law, drop these terms in, and we've got the electric field now expressed in terms of the magnetic field and the velocity of the plasma that we're looking at. But we wanted to, as I said, we're aiming, as hopefully you'll see why in a moment, to eliminate the electric field from Maxwell's third law, just going back. So Maxwell's third law, curl of E. So brilliant, we've got E now expressed in terms of magnetic field vector and velocity vector. So we take the curl of both sides of this and get an expression here that looks like a horrible mess of vector calculus, which it is, but it does work. We can then use some vector identities and the merciful div b equals 0 to rearrange all this and get the induction equation. So this is the change in magnetic field vector with time, dB by dt, expressed in terms of the magnetic field and the velocity only, with some constants. So this very, very speedy derivation, the aim of which is to simply show that it is possible to relate the velocity of a plasma to its magnetic field strength, to write down a differential equation for the magnetic field in terms of the magnetic field itself and the plasma velocity. So that's our equation of motion for magnetic fields in the interstellar medium, as it were. What other conditions apply in the interstellar medium? Well, firstly, conservation of mass, hopefully. Again, in some trouble if that doesn't apply. So we've got the mass continuity equation here, partial rho by partial t, where rho is density, is div of rho v. So that should be equal to 0. We've also got conservation of momentum. So that's expressed in terms of the Euler equation. We're ignoring viscosity for now because it makes our lives easy. And also it's not an unreasonable approximation. So here we've got this, and our terms on the right-hand side here are the body force per unit mass and the surface force per unit mass. So we've got body forces and surface forces. We're going to assume here that the body force term has gravitational and magnetic components. So we're going to break that force vector here down into gravitational force Fg and magnetic force Fb. And this is per unit mass. So magnetic force per unit mass, total magnetic force divided by the mass of your particle, which we can get like this. And you can work this through and get an expression for the magnetic force in terms of J and B and density. Going back to Maxwell's laws again, we can then get rid of our J and express the magnetic force in terms of per unit mass in terms of B rather than in terms of J. With some more unpleasant manipulation of these equations, we can get to a point where we've got an expression essentially writing the Euler equation in terms of the gravitational component here and these magnetic components. Again, I've done this far too fast. Absolutely not expecting anybody to have followed this as long as we went, but it is all there. So do please take a look afterwards. The point I'm trying to get to here is if we want to express the force balance in the interstellar medium and consider the magnetic fields, then we've got here an equation that lets us do it. We've got the magnetic pressure term up here. So this is saying that a gradient in magnetic pressure results in a net force on the plasma, which means that regions of the interstellar medium with a higher magnetic field strength than their surroundings will be overpressured and will expand. In exactly the same way that if you've got an overpressure in gas, just thinking in terms of gas pressure, that's our P there, you'd expect the same behavior. Magnetic fields will expand outwards to pressure equalize. So by analogy with thermodynamics, that gives us an expression for the magnetic energy within a volume V, and that is B squared V over 8 pi. I'm being awful here and using CGS units. If you want SI units, then that becomes you don't have to put in some mu naughts. So this gives us sort of an intuitive sense that magnetic fields can act as a pressure term in the interstellar medium, and also gives us an expression for the magnetic energy within a volume. We can also express this the ratio between the thermal pressure and the magnetic pressure, and this is known as plasma beta. So here we're just substituting nkt in for gas pressure, dividing through by b squared over 8 pi and getting these two regimes. So if beta here, plasma beta, is much greater than 1, we call it gas pressure dominated. And if beta is much less than 1, then the magnetic pressure dominates over the gas pressure. So that's one of the metrics by which we assess the dynamic importance of magnetic fields in the interstellar medium. The other term we have up here is the magnetic tension term. And what this does is provide a restoring force on a bent magnetic field line. So if we take a magnetic field line and ping it, what happens? Well, we can find out. So we'll take the simplest case here. So we've got a uniform, static, non-self-gravitating plasma. So we've dropped out the Fg term in the equations that we were looking at before, which has got some uniform magnetic field B naught in it. So we can write down a set of perturbations. We've got rho naught plus density perturbation, P naught plus pressure perturbation. Our initial velocity was 0, so we've just got the perturbation term here. And our magnetic field is the static value plus our perturbation. So these are our equations that's governing the dynamics, with the Euler equation here written in terms of the conservation of momentum written in terms of magnetic field. So mass continuity, induction equation, and Euler equation, those are our differential equations. And if you put those perturbations in and linearize, so drop all of the higher order terms, then you do get a relatively straightforward set of equations that we would need to solve to understand what's going to happen to this magnetic field as we perturb it in some small way. We want a differential equation, so we differentiate this with respect to time and substitute in our perturbed continuity and induction equations. So these two up here substituted into the differential of this one gets us a horrible differential equation. I solemnly swear I am going somewhere with this. And just to make our notation easier at the moment, we define this term here, which we call the alpha velocity. So this is a velocity vector along the magnetic field direction, as you can see here, because it's aligned with B naught. And at this moment, we're apparently doing this just to mean that we take some constants out of this equation. But it does give us something slightly cleaner to look at down here. So this being the velocity associated with the perturbation, and this being the velocity associated with the regular magnetic field that we have just apparently made up. This does, however, start to look like a wave equation. So we can consider cases where the perturbations vary in a wave-like way, which means that we can turn our d by dt's into minus I omegas and our grads into IKs. And you get this, which is a dispersion relation. So it is telling us how these propagations will move. That being said, I don't particularly want to solve that. So we're going to consider the very particular case where the perturbation is orthogonal to the magnetic field direction, which means that we can say that our Elfman velocity, which was along the magnetic field direction, dotted with the perturbation is 0, B naught dotted with the perturbation is also 0, and K dotted with our perturbation is also 0, which lets us drop out almost every term in this horrible mess, and just gives us this nice simple dispersion equation. And that means that the group velocity of a transverse wave propagating along a magnetic field direction is the Elfman velocity. So if you perturb magnetic fields, that transverse perturbation will propagate along the magnetic field lines at the Elfman velocity, B naught divided by 4 pi rho naught square rooted. So essentially, the Elfman speed, the Elfman velocity, determines how quickly a magnetic field can react to a perturbation. So it's analogous to the sound speed in a gas. If the magnetic field doesn't have time to react to a perturbation, then that's superalfenic. If it does have time, that's subalfenic, in the same way as we've got supersonic and subsonic when we're talking about sonic gas motions. So yep, the Elfman Mach number, it's the ratio of the speed of a non-thermal plasma flow and the Elfman speed. So very broadly speaking, for subalfenic velocities, we could expect the magnetic field to direct gas flows, and for superalfenic gas velocities, we might expect the gas flows to direct the magnetic field. So these are just two simulations showing the difference. We've got a subalfenic simulation over here with an Elfman Mach number of less than 1, and a superalfenic case over here with an Elfman Mach number greater than 1. And you can see on the left-hand side here, we've got pretty organized magnetic fields, which are not being significantly distorted by gas motions, whereas over here we've got a mess. The magnetic fields are very tangled, just moving as the gas moves. So going back to the induction equation, another important number associated with magnetic fields in the interstellar medium, and indeed in general, is the magnetic Reynolds number, which is breaking down these two terms in the induction equation into two halves. On the left hand here, we've got the diffusion term, which is the magnetic field diffusing through plasma. And on the right-hand side, we've got the advection term, which is bulk motion, so the magnetic field moving with the plasma flow. And the magnetic Reynolds number is essentially simplifying these down by saying, well, div, that's more or less the same as 1 over L. So we're turning this here into VB over L, and we're turning this side here into eta B divided by L squared. Is that a reasonable thing to do? I mean, there are worse approximations that we could make, and we get a magnetic Reynolds number, which depends on the length scale of the plasma that you're considering, L. So in the case where this magnetic Reynolds number is much, much less than 1, then we say it's diffusion dominated. And in the case that it's much greater than 1, we say that we're advection dominated. So which regime are we in the interstellar medium? I mean, the fundamental thing to remember here is space is big, right? Length scales in the interstellar medium are large. In most environments in the ISM, L is very large, and so the magnetic field evolution is advection dominated, and we can largely ignore the diffusion term here. And this is what's called ideal MHD. When you need to start worrying about the diffusion terms, which you do, it's generally not until really very small size scales in the interstellar medium. And we'll come to one of those cases at the end. So one more question you might realistically be wondering about is why does any of this matter if we're talking about particularly molecular clouds in which star formation is happening? Because fundamentally, molecular clouds are almost by definition neutral. The gas is molecular hydrogen, not known for being particularly highly ionized. Why should something that is very nearly entirely neutral care at all what the magnetic field is doing? So, I mean, this is related to the idea of flux freezing. So for a quantity, any quantity where this relation here holds, which is the one that we've been looking at for a while, it can be shown, I'm not going to, but it can be shown that the flux through a surface S is constant with time. So this is Alfvén's principle of flux freezing, that the magnetic field and the plasma should move together. On the other hand, our molecular clouds plasmas is the neutral interstellar medium of plasma. So whereas if we were confident we were in a fully ionized environment, you can twist your magnetic field up as much as you like, and the flux through a surface is going to stay the same. This still applies the large majority of the time in molecular clouds, and this is because of ion-neutral coupling. And this is because although molecular clouds are very much neutral, they are not 100% neutral. A very small amount of ionization does remain. I mean, this can be as low as 1 part in 10 to the minus 7 or lower when you get to the densest environments in the interstellar medium. But that is just enough to maintain a short mean free path for collisions between ions and neutrals. So fine, your ions are frozen to the magnetic field, perhaps. Your neutrals and your ions, they collide regularly enough for them to behave as a single fluid. So essentially all three have to move together regardless of the fact that the neutral gas shouldn't really care what the magnetic field is doing. It's that rate of collisions between ions and neutrals that maintains the flux freezing. That being said, ionization fractions do drop as you go deeper into molecular clouds, and eventually that does start to have an effect. And I'll come back to that again later on. So these are our key metrics. I've talked about plasma beta, magnetic pressure versus thermal pressure. I've talked about the alpha Mach number, magnetic fields versus non-thermal motions. I haven't, in the interest of time, derived this one up here, the mass to flux ratio, which is the relative importance of magnetic fields compared to gravity. If you're interested, I will add some extra slides on the Slack showing where this one comes from, because it is important. In fact, very often if we're talking about whether or not something is gravitationally bound and collapsing, it's the one that we want to know about. But essentially, it's in the same spirit as the other two. We're trying to work out which of these energy terms is larger in a given environment in the interstellar medium. Just one important thing to note, that environments in which the magnetic field is more important than gravity are called magnetically subcritical. Environments in which the magnetic field is less important than gravity are called magnetically supercritical. To my mind, that's completely upside down, but maybe it's a question of personal taste. But in all of these, what we're really looking for is the magnetic energy. How big is it? How does it compare to the other terms in the interstellar medium? Right, so that is the maths over. I realize I went through it at high velocity, but hopefully it's a useful reference. Topic is going to be, having told you that magnetic fields are there, present in the interstellar medium, that it's a magnetized fluid. How then do we measure those magnetic fields? Well, there's three main methods, and they all involve the polarization of light in various different ways. So we need to think both about linear polarization, where you've got you've got an ordered single electric field vector direction, and perpendicular to that, of course, the magnetic field vector direction. And we also have circular polarization, where we have that vector rotating as the light moves, as the wave propagates, sorry. These are quantified using the Stokes parameters. So this is a vector of sorts. We've got the total intensity detected up here, the linearly polarized intensity encoded in these Q and U parameters, and circularly polarized intensity is Stokes V. So this is the convention recommended by the IAU. Q encodes vertical and horizontal polarization, U encodes diagonal polarization, and V plus V is anti-clockwise, minus V is clockwise. That being said, Planck and a lot of cosmology works use this convention, with plus U going this way and minus U going that way. You just need to keep an eye on it because well, I very nearly published a wildly wrong map in a paper because I didn't realize how the Planck conventions worked. So just make sure you know which one your data is using if you find yourself using Stokes parameters for anything. As a non-cosmologist, I will say that this is the one the IAU has been recommending for more than 50 years, but there we go. So how do we actually measure the magnetic fields? How do we get our hands on these parameters? Well, the gold standard, the one that we'd use for everything, if only we could probably, is the Zeeman effect. So the Zeeman effect is our only direct measurement of magnetic field strengths in the interstellar medium. So it's a direct access to the line of sight component of the magnetic field, essentially through the splitting of spectral lines in the presence of a magnetic field. So you've got your single line here for a paramagnetic species. You can then split that up into a multiplet in the presence of a magnetic field. Unfortunately, magnetic fields in the interstellar medium are not particularly strong, and that splitting is not particularly large. So the Zeeman effect ends up inducing circular polarization along the line of sight, and much weaker linear polarization is induced in the plane of the sky. Unless you're looking at a maser, you're not going to be able to get the linear component. So we always see circular polarization giving us a line of sight magnetic field strength. This requires a species with a magnetic dipole moment if it's going to work at all. So paramagnetic species such as H1, OH, CN, there's claims for CCS and a couple of other species, but the range of species that can produce this effect and the range of critical densities associated with each of those species, it's not continuous across the entirety of the interstellar medium. And it's also very, very observationally intensive. That being said, in the next few years, there's going to be several new instruments that really might make measuring the Zeeman effect no longer quite as painful as it currently is. Another option is measuring Faraday rotation. So we're measuring the line of sight magnetic field component here, now through the rotation of background polarization. So you have your synchrotron emission in the background, you've got some material in between, and your polarization vector rotates in a way that depends on the magnetic field strength, the electron density, and the path length. This integral here is a quantity that's known as the rotation measure. So, I mean, the obvious problem here is that if you want to get this right, you need to know your path length through the interstellar medium, which when we're looking at the universe projected onto a sphere, is not necessarily straightforward, but can make some reasonable estimates and make use of this method. This is also excellent for extragalactic sources, but it's not suitable for high column density sight lines, such as molecular clouds in the Milky Way. And then we have the methods that I personally mostly use, which is dust emission or extinction polarimetry. So here we're looking at the linear polarization of light, and we're particularly looking at the linearly polarized emission of dust grains in the interstellar medium. So this mechanism is actually quite indirect. It's been known about since the late 1940s that dust grains in the interstellar medium preferentially emit light polarized perpendicular to the local magnetic field direction, and extinct light parallel to the local magnetic field direction. And the reason for that is because dust grains, at least some dust grains, align with their major axis perpendicular to the magnetic field direction. Why this happens has probably only been nailed down in the last decade or so, and there's still, ongoing discussion about the exact principles. But what seems to be going on is that the dust grains get hit by photons, which impart angular momentum to them. This starts them spinning, and if they have any paramagnetic inclusions, then this means that they can align with their mate. They end up precessing essentially around the magnetic field direction. So it's not a particularly direct mechanism, but it does work, and we can get from this a polarization angle and a polarization fraction. If we take that polarization angle and rotate it by 90 degrees, then that can tell us the magnetic field direction in the plane of the sky. So again, only one component, a different component than we were getting before. If you're interested in dust physics, there's a lot of information encoded in the polarization fraction, but if mostly going to be talking here about polarization angle. So yes, this is the summary for the various methods we have of measuring magnetic fields. We've got the Zeeman effect, which is our direct measure, but it requires a paramagnetic species and it's observationally intensive. We've got Faraday rotation, which measures the line of sight magnetic and field component. It requires measurements of electron density and path length, and it's not suitable for high column density sight lines. We've got dust polarization, which allows us to infer plane of sky magnetic field morphology. It can be used to map wide areas relatively quickly. I mean, I started out with an all sky dust polarization map from Planck, so it can do the whole sky. That being said, it's an indirect method, even more indirect than the others, and it is subject to a lot of complications, integration of signal along the line of sight, integration of signal within your telescope beam. And in certain environments, the grain alignment mechanism might change, in the vicinities of massive protostars, for example, or the grain alignment might just be lost altogether in the densest environments because, as I said, you need the photons present to spin the grains up in the first place. If you extinct all of your photons, there's nothing left to create this grain alignment. So there is extra bonus complexity in interpreting dust polarization observations. But these are most of what we use to understand magnetic fields in the interstellar medium. So then, we're using these methods to look at magnetic fields in clouds, in filaments, and in cores. What kind of things do we find out? So starting on the larger scale, there's various different models for molecular cloud formation. These are probably not as mutually exclusive as I've made them look here, but these include gravitational instability of the galactic disk, condensations from turbulence, and colliding flows. So the gravitational instability of the galactic disk, the first one here, which is sometimes known as Parker instability, is the one that most straightforwardly involves the magnetic field as sort of a crucial part of what's going on. So if we imagine we've got the galactic plane, that galactic plane has a magnetic field within it, and the weight of the gas above you is producing a gravitational force downwards towards the center of the plane. So let's presume that there's some gas volume that becomes a bit more buoyant somehow. This rises up above the plane into galactic halo. That buoyancy could be due to thermal feedback, cosmic ray propagation. It happens somehow in this mechanism. But the gas wants to move along the magnetic field line. So essentially, gas will then drain back down the magnetic field line while the magnetic field continues to sort of bloom outwards into the galactic halo. And this perturbation growth rate goes as what's called the Alphen crossing time, which is essentially the scale height of the galactic plane divided by the Alphen velocity. So if you say, well, the disk scale height is about 100 parsecs and our Alphen velocity is about 10 kilometers per second, this gives a perturbation growth rate of about, perturbation growth time of about 10 megayears. So, I mean, this is a cartoon. Sorry, this is a cartoon, obviously. Simulations, this is also reproduced in simulations. So these simulations suggest that if you've got a differentially rotating galactic disk, filamentary clouds formed in this way would form with their major axis perpendicular to the magnetic field direction in the plane of the galaxy. Unfortunately, as you'll see, magnetic fields perpendicular to density structure is the prediction of quite a lot of different models. We also have simulations of molecular clouds forming in condensations from large-scale turbulence. So this is a zoom-in simulation here. We've got our overdensity, zoom in and see more and more complexity as we go to higher and higher gas densities. In this case, the turbulence, driven by galactic rotation, clustered stellar feedback, creates shocks, which triggers thermal instability and local collapse. So these simulations can preserve sort of large-scale dynamics of turbulence and magnetic fields, investigate right the way down to small scales, but the sheer complexity of them means that it's not always easy to get straightforward predictions out of them for what exactly the magnetic field is going to be doing. We can, however, investigate more closely this idea of colliding flows. So this is creating density structure through converging flows of warm atomic gas. So converting warm neutral medium to cold neutral medium to molecular clouds. So there's a whole series of fluid instabilities that I'm not going to talk through in any great detail, but it's sort of this, you start out with something called the nonlinear thin shell instability, which induces shear. That shear transitions to turbulence via Kelvin-Helmholtz instability, those beautiful sort of wave-like cloud patterns that you occasionally see photographs of on the news. And then the condensations within the shock become thermally unstable, forming clumps of dense gas. Fine, so what's the magnetic field going to do to that situation? Generally speaking, make life difficult because that's what magnetic fields do. But in general, if the magnetic field is misaligned with respect to the gas flow, then dense gas formation is suppressed. So in these simulations, it's found that perpendicular or nearly perpendicular magnetic fields are required to the shock structure are required for star formation to happen. Again, same general morphology as the Parker instability model predicted, but now for an entirely different reason. There's a special case of this, which is where the reason for these shocks are shell expansions and interactions. So here you've got molecular gas forming in the interaction of expanding H2 regions or superbubbles. So stellar feedback creates an ionized region. If you've got multiple of those happening, then it's not unreasonable to expect sort of collisions of gas shells as your H2 regions expand. This is an example of one that's claimed in the very nearby interstellar medium. So here we've got two bubbles traced out, and here the corona australis molecular cloud. Coincidentally or otherwise, it depends who you ask, there are entirely different models for how corona australis formed, sitting velocity-wise and spatially in the interaction between those two shells. However, this interaction is difficult, or at least it's difficult to explain how you create molecular gas in a single interaction because timescales for cloud formation from the diffuse atomic medium are much greater than the predicted evolution time of a shell. And also, if the magnetic field is suppressing these instabilities, it's suppressing dense gas formation. And it's not obvious that the local magnetic field will always be aligned with exactly where your collision happens to be happening. So this, a way around this is the proposed multiple collision model. This paper by Shuoshio and Itsuka, where essentially you just keep doing this over and over again until eventually you form the dense gas. And again, these simulations produce sheet-like molecular clouds perpendicular to the large-scale magnetic field direction. So we need better observational tests here. I mean, it's unlikely that there's only one of these mechanisms that matter. Likely they're all playing a role. And we need, to be honest, better predictions for how to distinguish between them. Because if most predict similar magnetic field geometries, as you've seen, like if there's a prediction, it tends to be that the magnetic field will be perpendicular to the dense structure that's formed. We also need more measurements. So we need more measurements of magnetic field strength. And in these relatively diffuse environments, that means we need Zeeman measurements and we need Faraday rotation measurements of the cold neutral medium. There are groups working on this. This is an example of work by Behnush Tahani and collaborators looking at whether or not the magnetic field is wrapping around the Orion A cloud as measured by Faraday rotation, looking at the direction of the magnetic field on either side of the cloud. The multiple collision model does broadly match many of the observations, but that doesn't in any way preclude the other models from doing the same. It's just that one has probably produced the largest number of predictions. So there's a lot more work that needs to be done here, both observationally and theoretically, in understanding exactly what role the magnetic field is playing on these size scales. Okay, so we've got our molecular cloud. What then do we expect the magnetic field to be doing as the cloud evolves towards gravitational instability? So broadly speaking, the question here is, does magnetic field strength increase with gas density, or is the field being compressed by gravitational collapse? This is various different models of gas and magnetic field geometry from a paper by Tritsis et al. In 2015. The key ones I want to pick out here are sort of the two cases that are most commonly discussed, which is the strong field case, where the magnetic field is controlling dynamics, and the weak field case, in which the magnetic field is just along for the ride. So in the strong field case, what we're saying is that the magnetic field and the gas are frozen together. They're moving as a single fluid, perhaps. So that means that it's very, very difficult for material to move across magnetic field lines in the same way that, but very easy for the magnetic field, for gas to move along magnetic field lines. In the same way that if you imagine a set of guitar strings with beads threaded along them, like very easy to move those beads up and down the guitar string, no resistance there at all. If you try to take one of those beads and move them from one string to another, you'd have a fight on your hands. So essentially, where the magnetic field is important to the dynamics, material can flow freely along magnetic field lines, but not move across them, which means that material can collapse in along magnetic field lines, this case up here, and essentially not experience at least any magnetic resistance to the collapse, thereby forming dense structures, again, perpendicular to the magnetic field direction. When the cloud eventually begins to collapse across the magnetic field lines, the prediction is then that the magnetic field strength will increase as density to the power of half. So you've got two regimes in this strong field case, and one initially where the gas collapses freely along magnetic field lines. So the magnetic field strength doesn't increase as the gas density increases. And then we have this later stage at which the magnetic field strength goes as density to the half. Conversely, in the weak field case, if everything's just collapsing inwards homologously, then you expect magnetic field strength to go as density to the power 2/3. This was derived by Mestel in 1966. The useful thing here is that this prediction is unique to spherically symmetric collapse. So these two I've picked out here. The reason why I put all of these different geometries on this previous slide is to show that, as these authors showed in their paper, these aren't this one here, the collapse along magnetic field lines, isn't the only way that you can create B being independent of density. And similarly, we've got a different geometry here that produces B going as density to the power of half. But this one here is unique to spherically symmetric collapse. So fine, those are strong field and weak field predictions. What magnetic field strength do we measure as a function of density? So this is a plot published by Dick Crutcher in 2010, which compiled all of the Zeeman measurements, Zeeman because that's the one that actually directly measures magnetic field strength, and put them on a single set of axes. And what they found is that magnetic field is constant, our strong field behavior, below a density of about 300 particles per cubic centimeter. And then it goes as rho to the 0.65 above 300 particles per centimeter, which is our homologous infall value. So does that mean the problem's solved? You know, below this density, everything is strongly magnetized, magnetic fields controlling dynamics. Above this density, gravity wins, magnetic fields are relevant. I mean, this definitely indicates a trend, but it should be noted that firstly, 0.5 and 0.65 aren't hugely different numbers when you're dealing with data with error bars this size. And reanalyses have found indices in the range from 0.5 to 0.7. I mean, what 0.7 means in this context is, I think, anybody's guess. And this transition density here is right in between the critical densities where you can do well with H1 and the ones where you can do well with OH. So it's well within scope to fit something different here if you want to. And also, clouds aren't collapsing homologously on these size scales. So this is telling us something important about the point at which gravity takes over in molecular clouds, but it isn't, you know, smoking gun, problem solved. And there's a lot of work going on about how this relation is interpreted. So the alternative, if we don't want to work with magnetic field strengths, is look at the relationship between magnetic fields and density structure. And these, again, two simulations. Here we've got a simulation on the left with a weak initial magnetic field and a simulation on the right with a strong initial magnetic field. And what we see is that in the weak field case, as you would probably expect, the magnetic field just follows gas density structures around. So this is initially supercritical, so gravity initially winning, even from the start of the simulation, winning over magnetic energy. Conversely, over here, we start out with the magnetic field initially dynamically more important than gravity. And in the strong field case, what we find is that the dense structures, again, form perpendicular to the magnetic field direction for exactly the reason that I just outlined. And the transition here from parallel at low densities to perpendicular at high densities is somehow related to the transition to gravitational instability in these clouds. So this is an observation from Planck, and qualitatively, it does look a lot more like the case where the magnetic field is initially dynamically important than the case where the magnetic field is irrelevant at all densities. This is often codified using a tool called the histogram of relative orientations, which essentially takes all of that complexity and squashes it down onto two axes. On the x-axis here, column density. On the y-axis, something called the shape parameter, where if you're up in the top half of the plot, the magnetic field is preferentially parallel to density structure, and if you're in the bottom half of the plot, it's preferentially perpendicular. And in the strong field case, we expect an evolution from parallel down to perpendicular. And indeed, that is seen in some observations. Yeah, this is just what it looks like written down. You've got comparing the number of parallel measurements and the number of perpendicular measurements. This particular formulation does therefore ignore everything in the middle. So if you have a magnetic field that's 45 degrees your density structure, it doesn't go into this equation whatsoever. So there are alternatives, such as there's one called the projected Rayleigh statistic that takes the full range of angles into account. However, that doesn't necessarily mean that interpreting it in the context of understanding where a cloud transitions to gravitational instability is straightforward. So this is a plot that Ava compiled actually for our Protostars and Planets review a couple of years ago. So this is a collection of different simulations with the alpha Mach number of the simulation on the x-axis and the density, the transition density, where it flips from parallel to perpendicular on the y-axis. And I can see there's a 4 orders of magnitude change on this axis. So in some simulations, the flip happens at 100 particles per cubic centimeter. At some, it happens at 10 to the 6. And some of these simulations didn't have self-gravity in them, all of which means we need better observational constraints. We see this behavior in a lot of molecular clouds, but we don't always have a good handle on the volume density rather than the column density at which this transition happens. So, as ever, we need more observations, and we need more simulations to work out what it is here that's creating such a broad spread in the range of critical densities for the transition. That being said, can we get a magnetic field strength out of our dust polarization measurements? Because they are so much easier to make than all the rest of the methods I talked about. And the answer to that is maybe, sort of. So this method, the Davis-Chandrasekhar Fermi method, if you've never had the misfortune to work with it, there's 2 things you need to know about it. Firstly, it's definitive proof that it doesn't matter what you want to do in astrophysics, Chandrasekhar got there first and did it better than you. And secondly, it's a good way to start a fight in an empty room. So what we're doing here is working out the extent to which the magnetic field lines wobble. We're saying, well, let's assume that we've got an ordered underlying magnetic field. And we see magnetic field vectors that, even after we've accounted for measurement uncertainty, are not following that nice, straight, organized magnetic field that we think is there. Right, so those perturbations in the magnetic field direction are due, we are assuming, to turbulent motions pushing the magnetic field lines around. So essentially, if we can measure the dispersion in the magnetic field direction, we have a direct way of getting at the alpha Mach number. Maybe we do. We then pick so there's our alpha Mach number. We then pick a gas tracer, spectroscopic, get a line observation of this cloud from a gas tracer that we think is tracing the same material that the dust is tracing. Get its dispersion, get the non-thermal component of that dispersion, multiply out by that and say, brilliant, now we've got the alpha velocity. We then work out what we think the volume density is in our cloud. Never straightforward, but there you go. Multiply up by the square root of that. We then say, but we haven't accounted for the integration along the line of sight. We haven't dealt with the telescope, the fact that there's going to be integration inside the telescope beam, which is obviously finite. We need to correct for all of that. We'll multiply up by this Q factor, which is a correcting factor somewhere between 0 and 1. And then we say that we measured the plane of sky magnetic field strength. So the shock here isn't that this is not an exact measure of magnetic field strength. The shock is that it works at all, because it's not wildly wrong as far as we can tell. It's not right either, necessarily. So again, this is from our Protostars and Planets review. We compiled all of the measurements we could find between 2001 and 2021, stuck them on the same plot, and overplotted on here in the red dashed line the Crutcher relationship, which should be putting an upper limit on the magnetic field strengths in the interstellar medium. And they scale together better than we expected, frankly. I was terrified when we made this plot. But there you go. They at least fall roughly where we expect them to. I should also say that I've outlined the simplest possible version of doing this here. There have been a lot of attempts in recent years to improve this, either by adding in structure function ways of estimating the underlying distortion of the magnetic field, or there's some more radical reformulations recently making different assumptions about compressible or incompressible turbulence. Putting all this together, what we concluded was that at the level of calibration available over the last 20 years or so, DCF measurements of magnetic field strength do scale with the Zeeman measurements, our gold standard of as close as we can get to truth. But on average, they appear to overestimate the magnetic field strength by a factor between 3 and 5, which is not terrible by any means. But you don't know exactly what that factor is going to be in any given observation. And also, if we're interested in magnetic energy, then we're going to square the magnetic field strength. So if you're wrong by a factor of, 5 in magnetic field strength, maybe so what? But that means you're out by a factor of 25 in your magnetic energy density. So DCF, it's an important tool, it's a useful tool, but it needs to be treated as the approximation that it is. It's not a definitive measurement of magnetic field strength. That being said, I've got no intention of stopping using it because it continues to be the only game in town for measuring magnetic field strengths from dust polarization observations. And going back to this question of how dynamically important are magnetic fields in molecular clouds, both the histogram of relative orientation approach and DCF measurements suggest, at least based on Planck data, that molecular clouds are subcritical on large scales. So molecular clouds do have magnetic fields that are more important than gravity on the larger scales. So that does suggest that at least in some points in the interstellar medium, the magnetic fields are dynamically important, or at least dynamically important compared to gravity, which is worth knowing. But we can go and look on smaller scales. We can look at what magnetic fields are doing within the filamentary structures within clouds. And again, you'll notice a theme here. What they seem to be doing is aligning themselves perpendicular to the filaments. For all of the reasons that just outlined, if the magnetic field is dynamically important, we might expect gas flow along field lines down onto filamentary structures. So this is the torus B211 filament. It's about 140 parsecs away from us. It's unusually nice for a filament. It's about 10 parsecs long, ridiculously well organized, and it's got this very, very nice perpendicular magnetic field. Most filaments don't look that nice. This is an example from the Bistro survey, which I'm involved with, observing with the GISM3. So the image on the right here is the Planck scale magnetic field in this cloud. And again, you can maybe argue that the magnetic field is preferentially very, very broadly perpendicular to the density structures. But then when you come down and look at the magnetic fields within the individual filaments, it's no longer obvious that the magnetic fields are there perpendicular to the filament angles. So, I mean, does that mean that something wildly different is going on in this cloud? That we don't have the same sort of idea of self-gravitating filaments forming perpendicular to the magnetic fields? Well, not really. What we're dealing with here is the other bane of our lives in magnetic field studies, which is projection effects. We're looking at we're only looking at a single component here. We're looking at the projection of the plane of sky magnetic field, and we're seeing the density structure also projected onto the plane of the sky. So Yasuo Doi in this work showed that although we see a very broad range of relative orientations between the magnetic field directions and the filament angles, they're entirely consistent with being perpendicular to one another in 3 dimensions. And it's these sort of, I mean, I wouldn't go so far as to call this statistically significant sample, but it's this sort of edging in the direction of statistical significance that we've only been able to do recently with the larger numbers of measurements that have been made over the last few years. However, in high mass filaments, this is probably more complicated. So we've got these nice little going all the way back to torus here. This is a nice filament that's probably fragmenting along its length, like beads along a string, forming a series of dense cores. And that's what we see. On the other hand, in higher mass hub filament systems, what we might expect is that these filaments are no longer forming stars within them. They are sort of serving as accretion streams down onto a central dense hub where the massive star formation is happening. And what we tend to see in those cases is a magnetic field. You can see it here with the blue vectors, a magnetic field that changes again now to run parallel to the density structure, parallel to the filamentary structure, and is sort of a magnetized accretion flow down onto this dense central hub where the massive star formation is happening. So this is an example in Serpent South, published by Thushara Pillai a few years ago. But it's something that's seen in quite a lot of different molecular clouds. This is an example that I particularly like, though. This is the NGC 6334 region. So this is a massive, dense. Thank you. Thank you. Okay, so the what we have here is a central dense ridge with this whole host of filaments sort of radiating away around it. And what I particularly like here is that we see two different behaviors of the magnetic field depending on where we are along the filament. So not sure how well you can make this out here, but this filament 9 is a nice example. When you're well away from the dense ridge here, the magnetic field in this filament is perpendicular to the filament direction, which is the behavior that we expect for a low mass filament. But as you move along its length towards the, down the gravitational potential well, as it were, down towards the central dense ridge, the magnetic field rotates by 90 degrees to now run parallel to the filament. So these are the two behaviors that we expect to see in high mass star formation and low mass star formation happening in the same filament in the same cloud, which I think is at least a nice illustration that high mass and low mass star formation aren't necessarily as separate processes as we sometimes treat them as. Can I switch back to that one? Thank you. Sorry. Try not to tangle this up any more than I absolutely have to. There we go. Is that working? I'm trying. How about? No, my ears are clearly not the right shape. How about that? Right. No, gone again. I'm very sorry about this. I'm just going to. That working? Yes. Right. Let's pretend I didn't just try and put those on upside down. Thank you. Everyone, nobody saw that. No one saw a thing. Right. So moving swiftly on to pre-stellar cores. So the dense cores embedded within at least the low mass filaments that are to some extent, at least for low mass star formation, sort of a minimum unit of star formation, a gravitationally bound overdensity within a molecular cloud, which is going to go on to form either a single star or a single system of stars. So again, the definition here is argued. How do you know where one of these things starts, one of these things stops? But at some level in star formation, you have to have something gravitationally bound and collapsing. And a pre-stellar core is sort of a shorthand for that. So this is an example here of a Bok globule, possibly the most boring unit of star formation, just a sphere sat in the middle of nowhere, blissfully free of external influence. Most of them aren't like this, as you might expect. So there are many different ways of assessing the stability of one of these things. You can look at the virial stability. You can look at the Bonner-Ebert mass. A lot of it goes back to the Jeans equation, which I'm sure is painfully familiar, which is essentially saying that this is the mass at which gravity wins over thermal pressure. An object with where gravity wins over thermal pressure. If you think that turbulent motions can provide support against gravitational collapse, I believe the jury's still out, but I'll ask the people who actually understand turbulence about that one. Then in that case, you can sort of co-add in your non-thermal line width and bump up your Jeans mass a bit. But an object with a mass much greater than its Jeans mass should be collapsing under gravity. If it's not collapsing under gravity, then that suggests that there's another force involved with preventing that gravitational collapse, such as, for example, magnetic pressure. So if you see an object with a mass much, much greater than the Jeans mass that is not obviously collapsing under gravity, then the argument could be, well, therefore, maybe it's magnetically supported. So that's something to go out and look for. If, and this is by no means decided, if it's the case that these dense objects are significantly supported by their magnetic fields, then the sort of classical picture of a dense core collapsing in the presence of a strong magnetic field is mediated by a process called amber polar diffusion. So going back to the mathematical part at the beginning, I was talking about the magnetic Reynolds number, where we were looking at the importance of diffusion compared to advection. And I said, well, we don't need to worry about diffusion. Length scales in the interstellar medium are long. We're in an advection-dominated environment. This is the point at which maybe it stops being true, where you can start having the diffusion of magnetic field lines through, in this case, neutral material. So in this case, you'd start out with initially magnetically subcritical. So magnetic fields win over gravity, flux frozen, starless core. And I've just realized I've picked the worst possible combination for color blindness, so I do apologize. The red ones there are meant to be ions and the blue ones are meant to be neutrals. I will fix that because I should have spotted that one. So let's say that your ionization fraction has dropped, because we're in about the densest thing that you're going to get in the interstellar medium here. You're embedded deep within a molecular cloud. You've lost anything that might be going around ionizing particles. So the ion-neutral collision rate drops. And the ions and the neutrals decouple. So the ions are still frozen to the plasma, but the neutrals can do what they like, and what they do is drift inwards under gravity and creating an overdensity. And once the core becomes magnetically supercritical, once gravity wins, the ions start falling inwards too, and dragging the magnetic field along with them. So this creates this, what's called an hourglass morphology, sort of it's a characteristic indication of a magnetic field that used to be dynamically important, and now the object is collapsing under gravity. So a lot of time and effort has gone into looking at pre-stellar cores and seeing whether we see this or not. We expect this to be important when the amber polar diffusion timescale drops to be shorter than the free fall timescale in the core, which there's a lot of equations here, and I haven't defined the terms properly, but fundamentally depends on the ionization fraction, which depends on the cosmic ray ionization rate. So you can work out, if you think you know what your cosmic ray ionization rate is in a cloud, what you think your amber polar diffusion timescale ought to be. And it usually works out as a few times the free fall timescale in most environments. That being said, do we actually see hourglass fields in pre-stellar cores? And I would argue that in most, if not all of the ones we've looked at, we don't. So this is just a miscellaneous sample. We've got two cores in Ophiuchus here, one called L4183. This one it's in the Pipe Nebula somewhere. And they've got well-organized magnetic fields. They've got pretty linear magnetic fields. They do not obviously have hourglass morphologies. That being said, none of the sensitivities here are amazing. We're not getting out into the peripheries of the cores. So the extent to which they're just not there, or we're not sensitive to them, very much up for debate. It's not the case, however, that these hourglass fields never exist. So where we do see them is in interferometric observations of some, by no means all, protostellar cores. So this is the classic one. This is the one that got into Science, published in 2006, the low mass protostellar core, NGC 1333 IRS4A, lovely hourglass field. This is a massive cluster forming core observed with ALMA, and again, that hourglass morphology is seen in at least some cases. That being said, we have new and conflicting evidence about whether magnetic fields are actually important or not in these cores. So this is a technique that has been recently demonstrated using the FAST telescope, which I'll come back to in a moment. It's essentially a larger version of Arecibo, a 500-meter aperture telescope, which has been used to measure the Zeeman effect in H1 gas in self-absorption. So rather than looking at the Zeeman effect in H1 in emission, they're looking at the absorption of H1 against a background. So that means that they can get the Zeeman effect in density regimes that aren't usually available to H1. So this was looking at a dense core, very well studied dense core L1544. You've got the dense envelope here, where they got a magnetic field strength using OH, Zeeman, and then in the surrounding cold neutral medium envelope, they got a magnetic field strength using H1 in self-absorption. It's a really neat technique, and it suggests that the magnetic field is completely dynamically irrelevant. Essentially, they found that in the envelope, this is our mass to flux ratio here. So we get a subcritical mass to flux ratio in the very diffuse cold neutral medium. In the envelope of the core and in the core itself, they get high mass to flux ratios greater than 1. So this suggests that even by the time you get to the periphery of one of these cores, the magnetic field is already irrelevant. And it suggests that this particular dense core formed from gas that was already magnetically supercritical. So maybe the magnetic field stopped being important at some point earlier. That being said, this is one observation of one core, and it's not, and it'd be very interesting over the next few years to see more examples of this technique being used, so we can see the extent to which the magnetic field is or isn't dynamically relevant on these size scales and density scales. The other extremely contentious point is the existence or non-existence of high mass prestellar cores. So the high mass prestellar core argument is that high mass star formation is essentially a scaled up version of low mass star formation. You've got a large sphere of gas monolithically collapsing to form a single massive star. So if you want to do that, then you are going to need something with a mass much, much greater than its Jeans mass. And for that to happen, you're typically going to require a hefty magnetic field to prop it up. At any one time, there's usually a few high mass prestellar core candidates going, and I'm not sure there's yet been any definitively identified ones. Very often when you observe them in an interferometer, there turns out to be something embedded. But if these things exist at all, then they're almost certainly going to require extremely strong magnetic fields to allow them to exist. But the jury's still very much out on that one. Okay, so my last couple of sections are quite a bit shorter. I'm just briefly going to talk about magnetic fields and the interaction with feedback. So this is something that's been sort of increasingly studied over the last couple of years or so. So we have here two simulations of outflows from protostars. The one on the left is in the absence of a magnetic field, and the one on the right is in the presence of a magnetic field. And in this particular case, the star formation is more clustered in the absence of a magnetic field, and the outflows don't propagate so far into the cloud. So some, by no means all, theorists suggest that magnetic fields might play an important role in setting the star formation efficiency of a cloud, not through any direct effect, but through their coupling with feedback. So Within a star-forming core, magnetic fields and feedback play a role in removing mass and angular momentum, preventing further accretion. And over entire molecular clouds, the idea is that they might propagate outflow feedback over larger distances than would be possible in the absence of magnetic fields, thereby sort of inducing extra turbulent motion over large volumes. There are various observational efforts ongoing to work out the extent to which magnetic fields are correlated with outflow feedback, which I didn't include in the interest of time, but very happy to talk about it. Another possibility is the interaction between magnetic fields and stellar feedback. So here, H2 regions, photons from massive stars. And we've got two simulations here in the present without a magnetic field and in the presence of a magnetic field. And what seems to be happening in this simulation is the magnetic field is providing an extra tension term, essentially, preventing the breakout of the H2 region. So there's the suggestion that magnetic fields may play a role in the confinement of H2 regions. What we tend to see is that under feedback, magnetic fields run parallel to perpendicular to wherever the photons are coming from and parallel to photodissociation regions that we're tending to detect them in. So this is NGC6334 up again, where we see approximately concentric magnetic field patterns around H2 regions, perhaps suggesting magnetic fields compressed as the H2 region expands. This is the Orion bar, which is an edge-on photodissociation region bordering the trapezium cluster, and we seem to see the magnetic field running parallel to the length of the bar. So we tend to see magnetic fields in the presence of feedback being very substantially reordered in our admittedly limited sample so far. Okay, so jumping up size scales wildly, I'm very briefly going to talk about galactic scale magnetic fields. So in spiral galaxies, at least, magnetic fields run along the spiral arms. The idea is that the magnetic fields are initially generated by small scale turbulent dynamos, and then the galactic rotation sort of amplifies and maintains the field in this galactic dynamo model. And if anyone asks me any questions about this, I will ask Ava. But those magnetic fields are there. Spiral galaxies have ordered magnetic fields on the size scale of galaxies. These are being increasingly mapped. The main driver here is the Sophia Salsa survey, which was led by Enrique Lopez Rodriguez. Got a little rogues gallery here of magnetic fields in various different external galaxies at various different wavelengths. Some of the nice clear ones here, like M83, you can really see the spiral structure, and you can see the magnetic fields following the spiral arms. That being said, star formation feedback appears to be able to disrupt the fields on galaxy scales. So this is a particularly dramatic example, M82, the nearest starburst galaxy. It's got this ridiculous starburst going on in its center that's driving a super wind that extends 11 kiloparsecs above and below the plane of the galaxy. And what we saw when we observed its magnetic field is that where that starburst is going on, the magnetic field has been rearranged away from being aligned with the spiral arms of the galaxy to being entirely poloidal and directed out of the plane of the galaxy, which it turns out that Terry Jones predicted back in 2000. At least it's nice that it's what we saw in observations as well. And to be honest, I'm not going to say a huge amount more about galaxy scale magnetic fields because I only have a passing acquaintance with them, but there are a lot of problems out there. And if you're interested, I'd suggest looking at this review article. These include sort of mismatched spiral arms of magnetic arms, looking at magnetic fields aligning with warped disks, just been talking about the starburst driven. And there's also a huge amount of work to be done on the relationship between magnetic fields observed at radio wavelengths and those observed in dust polarization. So we've got this example here of two interacting galaxies where the far infrared dust magnetic field bears no real relationship to the field observed at radio wavelengths. So there's a whole host of questions to be answered there that, are starting to be accessible now that it's possible to observe magnetic fields in galaxies other than our own in this way. Which brings me on to my final point, which is how do you actually get hold of a telescope that can tell you something about any of this? I called this section Future Facilities, and then I thought it's not fair to just jump straight to the future facilities without talking about what we've got at the moment. So if you're interested in dust emission polarimetry, the James Clerk Maxwell Telescope has been making a lot of running over the last few years. I have to say that I'm on the telescope board, but it really has been. The IRAM 30-meter telescope has its new NICA 2 polarization sensitive camera, and there's going to be some really exciting results coming out of that. I haven't got it on this slide, but the Toltec camera on the LMT, when it's commissioned, will do the same. And ALMA has absolutely revolutionized our ability to measure magnetic fields in high mass star forming regions at high resolution in other galaxies. It's been absolutely phenomenal. ALMA should also be able to do Zeeman splitting. So far it's racked up an impressive catalogue of non-detections, but it is in principle possible. And the wideband sensitivity upgrade for ALMA, one of the fringe benefits of that is hopefully going to be giving it the sensitivity it needs to get at the Zeeman effect. If you're interested in Zeeman splitting, I mean, these are not all of the telescopes available to you, but we've got the Meerkat array, which is coming online in South Africa, and FAST, the 500-meter aperture rate telescope that I mentioned a while ago, which is in China. For Faraday rotation, again, I've just picked out a couple here: interferometers, ASCAP down in Australia, Effelsberg. There are others that can do Faraday rotation for you. So I'm going to talk about future facilities, but you don't need to wait for the future. These are all here right now. And if you're not able to apply for time on them, then find someone who can. All of these have different sort of affiliation requirements, but there's a lot of telescopes out there that are giving us all the data that I've been showing over this talk. Also, I should mention, special mention for the JCMT. As far as I know, the only telescope literally stolen by pirates. I'm not talking about data theft, literal piracy. It's a great story. So that being said, what's coming up? So I'm just going to talk about 3 possibilities. There are probably more, one of which is PRIMA, Probe Far Infrared Mission for Astrophysics. So this is currently undergoing phase A study, 12-month mission concept study underway. It would be launched by NASA. It would essentially do the same thing as the Sophia telescope that closed a little while ago, but with a really outrageous increase in sensitivity. So this plot here is something we knocked together for a paper, just demonstrating how good it would be. Up here is what we would see with Planck in the Ophiuchus cloud, and this is what we think we would be able to see with PRIMA. So essentially, if you could observe it in total intensity with Herschel, you'd be able to observe it in polarized light with PRIMA. That being said, this is very much hostage to NASA budget decisions, but I don't think anyone here has any control over that. So, if it happens, it will be absolutely phenomenal. Another concept is ATLAST, so the Atacama Large Aperture Submillimeter Telescope. So the JCMT, which I mentioned several times, is a 15-meter telescope, and it's the largest submillimeter telescope in the world, and it has been since 1987. We are overdue for an upgrade. ATLAST, it's targeting 50 rather than 15 meters with a 1 square degree field of view. Interestingly, they're also aiming to be the first fully sustainable telescope. And there's currently a Horizon Europe funded design consolidation study underway. They're aiming for first light in the mid-2030s, but as yet no one has actually agreed to pay for it. So it's also somewhat nebulous. That being said, something that is happening, definitely happening, is the Square Kilometre Array. So this is under construction right now in Australia and South Africa. Meerkat that I just showed you is going to be folded into the South African mid-frequency component. So I am very excited about the Square Kilometre Array, and because it's going to be suitable for measuring the Zeeman H1, OH, H1 in self-absorption. It's going to be good for Faraday rotation. This is why, when I said earlier, like Zeeman is going to become considerably, hopefully, less arcane in the next few years. This is why, because we are going to have this incredible facility available to us that will really, I think, change in a big way our quantitative understanding of magnetic field strengths in the interstellar medium. And I think now is probably the time to start getting involved with this, because the first very early science data is only expected in a couple of years now. So there's a lot of great facilities you can use right now. There's a lot of great facilities coming down the line. And there's a lot of questions we still have to answer. So thank you very much.
Yes, thank you very much, Kate. Perfectly on time as well. Are there questions for Kate?
Thank you for the nice talk. I was wondering, in the cloud formation scenarios where you showed that the collapse happens preferentially along the magnetic field lines, what happens to the net angular momentum that the forming clouds might have?
That is an excellent question. Well, it must go somewhere. I mean, that is sort of very simplified picture in which everything is just falling linearly along linear magnetic fields. In reality, that nice simple picture ignores the turbulent gas motions as well. So I was talking as if you've just got supercritical and subcritical magnetic fields, and gravity and magnetism are the only thing that matters. But in reality, all of this is happening in a turbulent interstellar medium, right? And I've said nothing in any of that about what the alpha and Mach number is. And so in reality, that nice simple picture is probably wildly understating the complexity of what's going on. So I think probably I'm waving my hands and saying turbulence in the way that most people wave their hands and say magnetic fields, but I suspect that the answer is the turbulence of the clouds. Ava, you've got your hand up. Yeah. Oh, okay. Sorry, I thought you were answering.
Does anyone know about the angular momentum thing? I think it's one of the hardest things to ask. No, my question was different, and it regards this magnetic field density relation. So consistently in every simulation I can remember, we see one single power law all the way down to low densities and column densities. And it looks that the data support that too. So are we ready to abandon the Crutcher broken like line thing?
I mean, I think you'll find it hard to get the observers to abandon it because that being said, I think like that relation, it's not based on that many data points, right? And the error bars are large. It's very much the H1 measurements that are driving up that behavior and just at that one end. So I will be really interested to see what we see with Zeeman like with the SKA and with when we get more Zeeman measurements out of FAST, because I'd hope that we can really up the sample size, fill in that plane, and see whether continues to behave like that. Because I mean, also with the compilation of data there in the Crutcher plot, I mean, it is a compilation, right? It's lots of data taken with different telescopes, all over plotted on the same set of axes. So, and different telescopes will have observed the different wavelengths. So I don't know, but I think a really good observing campaign with one of these newer instruments could answer observationally what's going on there.
Other questions for Kate?
Yes. I wanted to know a little more about how do we understand what is happening along the line of sight with the dust emission lines? Is there any way to do that?
It depends who you ask. So there are arguments made that we can get some handle on the 3D structure of the magnetic field by looking at the polarization fraction. So the polarization angle gives us the plane of sky sort of average along the line of sight, but if the magnetic field were more along the line of sight, then we would expect a lower polarization fraction. If it were more in the plane of sky, we'd expect a higher polarization fraction, all else being equal. Unfortunately, polarization fraction is an absolutely terrible quantity. It's got non-Gaussian noise. It's also influenced by the grain alignment, like how well the grains are aligned with the magnetic field. So applying that in practice is very difficult, but at least in theory, there is some information available about the line of sight magnetic field from dust observations, but it's difficult. Ideally, what we'd want is even observations of a dense tracer along the same line of sight.
Jerome.
So polarization measurements are done mostly in continuum. And so what's the effect of the large-scale filtering of the instrument?
Significant. So this is a big problem, as I understand it, with the Planck observations, in that you're looking at the entire column of the galaxy, and it's not always clear how deep we're able to go. For ground-based data, like the JCMT data, because of the need to account for the effects of the atmosphere, a quirk of that is that we're completely insensitive to large-scale structure. So we don't need to worry about filtering out the large-scale emission just because we can't detect it anyway. The atmosphere filters it for us. For interferometric data, of course, the filtering is set by the how you fill in the UV plane. So getting all of the spatial scales is difficult. The best thing that we could do is sort of feather together. So there has been talk about sort of feathering together ALMA and SMA and JCMT data and trying to at least get some level of continuous structure. But at the moment, I don't think there's anything that can bridge the gap between sort of scales traced by the JCMT or IRAM and those traced by Planck. There's a gap there we can't fill in with current instruments, which is why we should put a polarimeter in space, in case anyone has control over the NASA budget.
Okay, I've got. Oh, sorry. Wait for my question.
Very nice. So I have a follow-up question about how does large-scale filtering works on the polarized intensity? Does that act the same as the total intensity? Just remove the fraction of flux, or like other effect on the polarization?
It depends on your instrument, I think. So as I understand it, for interferometric instruments, large-scale filtering tends to be worse for Stokes I than it is for total intensity than it is for Q and U, which results in polarization fractions being even harder to trust than they otherwise would be. For the single dish data, I don't, as far as I'm aware, that all of the different polarization components are affected equally, but it will very much depend instrument to instrument, I think.
Thank you.
So I had a couple of questions. Do you want to come back to the slide about the outflows, where you talked about that you compared the different simulations with and without magnetic field?
Yep.
I just wanted to, and you made a statement that the magnetic field helps propagate the feedback.
May do.
May do. I just like to invite you to expand that concept of propagate in a more physically as to how that would work.
In as much as I understand it, the idea is that so when you have the outflow, you've got magnetic field lines sort of entrained, got a helical magnetic field associated with the outflow, which would then, because the field lines have to join up somewhere, connect to the magnetic field of the surrounding cloud, making it easier for ionized material to flow out into the cloud, is my very naive understanding of what they're going for.
Okay. And then I'm going to ask another question. So I think it's the first magnetic field in external galaxies talk where I haven't heard people talk about the synchrotron polarization.
Personal bias. Yeah.
So again, just a comment you made about how the radio polarization and dust polarization vectors do not quite agree. So perhaps for the benefit of the people in the audience who, why is that expectation either surprising or not very surprising?
So they should be tracing different densities, right? So synchrotron emission will be tracing lower density material, perhaps the sort of around the galaxy, whereas the dust polarization should be really tracing the dense material in the plane of the galaxy. And me not talking about synchrotron emission is entirely my own preference for working at higher densities. But it is interesting, and this is actually, it's still not talking about synchrotron emission, but it's something interesting that we saw when we were observing M82, that even looking at different wavelengths in the dust, we saw different behaviors. So looking at the 850 micron data, very, very preferentially tracing cold stuff in the plane of the galaxy, we saw the field sort of aligned with the galactic dynamo as we expected in the periphery, and then the poloidal one in the edges, sorry, in the center. When we looked at the Sophia data, they just saw the poloidal field. So they were tracing hotter dust, probably entrained in the outflow, and seeing the poloidal field out to much greater galactocentric radii. And where we saw the break in behavior was exactly the scale height of the dust in the galaxy. So yeah, I don't think it's surprising that they don't agree, but I think it means there's something more to be explored there about dynamically what's actually happening.
Right.
Are there people that are trying to do 3D, reconstructing the 3D structure of the magnetic field, a bit like the volume density is done with Gaia?
There are people trying to do, so there are definitely people looking at it. One interesting thing that I didn't really have time to talk about here is using extinction polarization rather than emission polarization. And that's got a very powerful sort of synthesis with Gaia observations, because the extinction polarization, you're looking at how background starlight is extincted as it comes towards you. So if you know how far away those stars are, and you've got the extinction, you can construct how the magnetic field varies essentially as you move through the column of the Milky Way towards the background star. So I think it's Yasuo Doi has been leading some work on this, trying to sort of construct layers of magnetic field as you move away from us into the galaxy. So work is definitely being done on that. Yeah. for just constructing 3D magnetic fields within say an individual cloud. I mean, there's various different ways you can try it. You know, there's looking at the polarization fraction. There's looking at trying to combine together the Zeeman measurements of line of sight field and the plane of sky component. There's also some interesting work that looking at different wavelengths of, like looking at polarization but at different wavelengths. So looking at the different optical depths as you go to different wavelengths. So for example, looking at the Sophia 214 micron data, that's got a much higher optical depth than the 850 micron data does. So in principle, you could look at magnetic field and sort of surface of the cloud and integrate it through the entire cloud and look at the differences. So there's definitely work being done on it.
Final question for Kate before we break for coffee.
If there's not, I'll tell the JCMT stolen by pirates story if anyone wants to hear it.
I think we want to hear it.
So I've been told this by reliable sources, which is not necessarily true of everybody who was there at the time. So the JCMT, at least its outer paneling, was built in Bolton in the north of England and then shipped to Hawaii. But the contractor that was going to ship it out there fell through. And they just had to grab the nearest available person who said they could ship their telescope out of frame to the other side of the world. So they piled this all on a boat at Liverpool docks and sent it off. And then they vanished. And this was the 1980s, so you could only find out where someone was by looking at shipping logs, you know. So they watched this boat wandering between ports around South America for a while. Eventually went through the Panama Canal weeks and weeks late. Got to Hawaii, and at this point they were so late that they were going to lose more money on the late fees than they were going to make on the job. So apparently the captain radioed ashore and said, "Promise to pay us in full or we'll just throw it all in the sea." But because this was international waters, they called the US Coast Guard, got it declared as international piracy, and the US Coast Guard stormed the boat and got the telescope back. But I mean, it's a serious point about, because when the James Webb telescope was shipped to French Guiana for launch, it was in absolute secrecy. You know, when it went through the Panama Canal, no one knew where it was because it's worth billions of dollars. It's irreplaceable, and you just put it on a boat. You know, I mean, admittedly, you're then going to put it on top of a rocket, but so I'm sure there's a very interesting problem out there on insurance of mega projects. But I think the moral of the story is choose your shipping company carefully.
Okay, thanks very much, Kate, for this amusing story and for the lecture. Were there any announcements? So we're going to projects, hands-on afterwards. It's just our group that's in TP. So group 4, you'll be in TP1 today, just for today. And group 3, you'll be in here. Okay. All right, thanks everybody.